Hey guys, we've gone through dozens of past midterm tests and exams, and we've picked out the 4 most common questions that are likely to show up on your calculus midterm. So let's get to it. The first type of question is a limit that involves the conjugate. What that means is that we can't plug in x equals 4 because the bottom's going to 0, which we cannot have. But our x on top is trapped under a square root. So we have to multiply top and bottom by the conjugate, which just means the exact same thing as the top, but change the sign in between. So I'm going to multiply by root x plus 5 plus 3 over the same thing, root x plus 5 plus 3. What that does is that gets rid of the square root on top. Don't multiply out the bottom. But let's see what happens. We get this equals the limit as x goes to 4 of x plus 5 minus 9, because it's minus 3 times 3 and the middle terms cancel. Our square roots are gone, and on the bottom we will not multiply out, so we've got this. Now we can simplify the top, and that will cancel our problem bracket on the bottom. This equals the limit. Don't forget to write limit. X goes to 4 of x minus 4 over x minus 4 times x plus 5 plus 3. Now we can cancel. This cancels with this. Our problem is gone on the bottom, so we can just sub in 4. We're left with 1 on the top, sub in 4, and we get the square root of 4 plus 5 plus 3. That equals 1 over the square root of 9 plus 3, which equals 1 over 6. Super simple to pick these questions out because your x is trapped under the square root. Multiply the conjugate to get rid of the square roots, and then cancel the term that's causing the 0 on the bottom. This question's super common when they're asking us to find dy by dx, or the first derivative of a function that has a product rule within a chain rule. And what that means is there's 2 functions that are multiplied together within a bracket that's raised to a power. So we need to work from the outside in, and this becomes a really simple question. I'm going to bring the 4 down and blindly copy the bracket raised to the power of 3, always 1 less than the power it started with. So 5 root x tan x raised to the power of 3. Then we multiply by the derivative of what's inside. Well, what's inside is a product rule. So I'm going to look at 5 root x as the first term and tan x as the second term. Then I know the product rule is the derivative of the first times the second. So multiply by the derivative of the first is 5 times 1/2 times x to the negative 1/2. That's the derivative of the square root of x, because the square root is like having an exponent of 1/2. Then you multiply by the second term, tan x, plus the derivative of the second term, secant squared x is the derivative of tan x, times the first as is. Close the big bracket, and you're done. Here's a continuity question. We're asked to find m so that f of x, which is a piecewise function, is continuous everywhere. Notice that both the functions, this is a quadratic and a line, those are continuous everywhere, so the only x value we need to test for continuity is the breaking point, which is 2. So our entire goal is to show that f of 2, the function at 2, equals the limit as x approaches 2 of the function. Now f of 2 is really easy to solve. We just plug 2 into the top equation because that's the equation we use when x is equal to 2. So we can say f of 2 equals m squared minus 2 squared, which is 4. That's great. Now we've got to show that the limit exists, and that to do that we have to show it equals the same from the left and from the right. So the limit as x approaches 2 from the left of f of x, I'm going to use the top equation again because that's where x is less than 2, so from the left. This equals m squared minus 4, because I'm plugging 2 in for x. And the limit as x approaches 2 from the right of f of x, I'm going to use the bottom equation because that's where x is greater than 2, so it's coming from the right. That's going to be m minus 2 because I'm plugging in 2. The last thing we have to show is where are these equal? What value of m makes these two equal? just set them equal to each other. M squared minus 4 equals M minus 2. That's a quadratic, everything to one side. M squared minus M minus 2 equals 0. And then we can just factor the quadratic. So it's M minus 2, M plus 1 equals 0. So M must equal 2 to make that bracket 0, or negative 1 to make that bracket 0. So M equals 2, or M equals negative 1. These would be the values that make this function f of x continuous everywhere. They love asking questions on the intermediate value theorem without actually asking for the intermediate value theorem. All they're saying is show that there's a solution to this equation, so sine x minus 0.55 has to equal 0. Show that there's some value of x that makes that happen over a particular interval. So we could actually solve for x, but what they actually want us to show over this interval are a value that makes this expression less than 0, so negative, and a value in the interval that makes the expression greater than 0. Because we know this expression is continuous over that interval, we know that if we can show part of it is negative, part of it's positive, it must cross the x-axis and be equal to 0 somewhere in there. So all we need to do is pick a value in the interval that makes it negative, pick a value that makes it positive, and we've proved it. So I'm just going to go to, let's say, pi over 6. So I know that sine of pi over 6 minus 0.55, that equals sine of pi over 6 is 1/2, so that's 0.5 minus 0.55, and that is a negative value, negative 0.05. So I've shown that at pi over 6, which is in this interval, it's negative. Now I need to show somewhere that it's positive. Well, I know sine, let's take pi over 3 minus 0.55. Sine of pi over 3 is root 3 over 2 minus 0.55. I don't know root 3 over 2 completely off the top of my head. It's higher than 0.8, I know. So I know this is greater than 0. And therefore, by the intermediate value theorem, I've shown one spot where it's positive, one spot where it's negative, and it's continuous over this interval, so there must be at least one solution.